So let us begin with the special register. The first one is Program Status Register, PSR. In that one, there are multiple types are there in PSR. We'll see one by one. The special registers in the Cortex M3 processor include the following. One is PSR, that is Program Status Register. Second one is Interrupt Mask Register. In that one, Primary Mask, Fault Mask, and also Base Primary Mask. Third one is Control Register. Special registers can only be accessed via MSR and MRS instruction. MSR and MRS. That means memory to register, register to memory. Memory to register, register to memory, will call that one. Even we are having two more instructions like LDR and STR. LDR and STR is not same as MSR and MRS. Okay. Memory to register and register to memory, whenever we deal with, at that time we go for the MSR and MRS instruction. They do not have the memory addresses. They don't deal with the memory addresses. See, they are given a simple instruction, a prototype, MRS, register, special register. MRS, register, special register is what they have given. What exactly will do? The instruction MRS, usually I always prefer writing the instruction in capital letters. Writing the instruction in capital letters. MRS and the first one, then we are going to give the actual general purpose register, comma, the special register. The syntax is like this. MRS is the instruction and two operands what we are giving is, the first operand is the register and the second operand is the special register. Always we know that in programming languages, the instruction whenever you are going to write the instruction, it will always perform from right to left only. Right to left. Whichever is right, from there to left. I'm adding the right operand. From the right operand, it will read and it's going to write into the first operand whatever you have given over. So what this instruction is going to indicate? Read from the special register. A special register is there. Read from that one. Then whatever you are going to read that one, that will be dumped into the general purpose register. Okay. So read special register and whatever you read, that will be stored, or that will be loaded. I cannot say stored, that will be loaded into the general purpose register. Similarly, we are adding one more instruction, that is MSR. MSR is reverse process of your MRS. Getting very simple. Okay. MSR is read from the special register and dump it into the actual your general purpose register. MSR is the reverse process of MRS, where it will write into the special register. From the general purpose register, it will write into the special register. Okay. So we are adding a special registers. From the special register, it is going to read by using MRS, and that will load into the general purpose register. The second instruction, whatever is there in the general purpose register, that will be stores back into the special register itself. Now let us see, the one of the important topic of your Cortex is program status register. As I said, it will give you the entire details of what is the current status of the program. The PSR, the program status registers are subdivided into three status register. One is APSR, second one is IPSR, and third one is EPSR. What is APSR? Application Program Status Register. Application Program Status Register. IPSR indicates that one interrupt program status register, and EPSR execution program status register. These are the three subcategories of your PSR. The three PSRs can be accessed together or separately using the special register access using MRS or MSR. Whenever you want to deal with the APSR, IPSR and EPSR, you are going to use the instruction called MSR or MRS. Because PSR is a special purpose register, you need to know that. When they are accessed as a collective item, the name XSPSR is used. See, generally we are having PSR that is subdivided into three types. When we want to perform individually, you will be using it as APSR, or you will be using it as IPSR, or you will be using it as EPSR. But when we want to put them together and execute at one single point, we are going to use it as a XSPSR. Okay. So individually we can also do execute, or we can put together at a single point, we can execute that one. That is using XPSR. X indicates all. You know that one. There is, we were having 80x86. 80x86. X indicates all. Means 80286, 80386, 80486, Pentium, Pentium 1, Pentium 2, Pentium 3, all those things come into the picture. X indicates it is general. General includes all the values of this. 8086 was the first. 8086 was the first microprocessor. It was the first microprocessor. Before that, we had 8085, 4004, all those things. But once 8086 has come, new versions has come into picture with the upgradation. Then they have made it as 80286, 80386, 80486, like this. So the instruction set or the application, if it is capable of handling all these things, they used to represent like 80x86. Means all family, entire family can deal with. Similarly, when I am coming with respect to PSR, that is program status register, if I am able to execute all the three types of PSRs, then instead of mentioning individually, I am going to use X as the indication for dealing with all. All the three types of PSRs can be operated. It will consider. Okay. Program status registers, you can read the PSRs using the MRS. MRS is for reading. Okay. You can also change the APSR using the MSR instruction. Means you want to write into that. Then you can go for MSR. But EPSR and IPSR are read only. See, very, very important. PSR, it is subdivided into APSR, IPSR and EPSR. We can modify APSR by using MRS and MSR instruction. MRS is for reading, MSR is for updating or modifying. But IPSR and EPSR, these are the two special registers which can be read only. I cannot modify that one. As the name says, APSR is the application program status register. I can modify it. But interrupt cannot be modified, execution cannot be modified. Execution is only read only, interrupt is only read only. If any interrupt comes into picture, I cannot modify the interrupt, I can only handle that interrupt. So, interrupt program status register, execution program status register cannot be modified. We can only read only using your read instruction. Okay, but if you want to write, only APSR is possible. We cannot modify the EPSR and IPSR. See here, MRS is for read. MRS is for read. Read from APSR and load that one. Whatever you are reading, load that one to a register or not. Assume that one command in APSR. Command the value for 55. Some value command. Just for application purpose I am using. APSR is a special purpose register. In that one command the value 55. I can read that one by using MRS. I can. So what is there in APSR? The value of APSR will be dumped into R0. So now R0 can be value 55. Similarly, I can go for IPSR also. I can go for EPSR also. I can use any resistor. I can use any resistor here where I can read, I can dump it over. I can read and dump it. But the last instruction what it is showing, we can only modify APSR, we cannot modify IPSR and EPSR. So MSR is the instruction used to store back into your special purpose register. That is MSR. I'm going to use from here. That is APSR. Anything, whatever is there in R7, that will be dumped into APSR. What exactly it is performing is showing the so read from APSR, load into R0, read from IPSR, load into R0, read from EPSR, load into R0. R0 is overwriting here. But later from R0, whatever the result has come in R0, that will be stored back into APSR, write flag state. Very important, this block. As we all know that one, the size of the register is of 32 bit. Correct? Every register is a 32-bit register. Every register in your ARM Cortex M3, the size of the register is 32-bit. Even PSR also 32-bit register. What exactly is there in 32-bit? How exactly it deals with all the 32-bit which is available in the PSR? Okay, so starting from 0 to 31, we see APSR how it looks, IPSR how it looks, and EPSR also. Most of the time, the last one we prefer, XPSR. That is XPSR indicates all the type of the special purpose register. It indicates AP, that is application, interrupt, and also application, interrupt, and also execution. All three put together, we are going to call XPSR. Now, if you write the second block, that is okay. Or you want more details, you can go for the first block also. The top one. Second one is almost, it covers everything. The second one which is there on the slide, all the 32 bits are indicated. Instead of writing, I'll explain here itself. We have NZCVQ. Are you able to see NZCVQ? Is there NZCVQ is there on the screen? Yes, correct. What is N? What is Z? What is C? What is V? It's an individual bit of the program status register. Individual bit. 32 bits are there. All the 32 bits are in different notations. Now, very important. This is a definite question in the examination. With a bit format, explain the PSR. Explain the PSR. So what you have to do, you should write 32-bit format, you should write. And left side you are having NZCVQ. NZCVQ is very, very important. What NZCVQ indicates? N indicates negative, Z indicates 0, C indicates carry, V indicates overflow, Q is a special flag. These are all the flag registers. Flags which are available 32, 32nd and 31st bit, the MSB. MSB, it is 32 bit or 31, bit number 31. It indicates N. N indicates negative. Can someone take the calculator? I want you to do that. I want you to do that. Yes. Okay. Now, I want you to convert the decimal into binary. Decimal into binary, I want you to convert. I'll give the value 65,535. Decimal value I'm giving 65,535. Convert that one into binary. Convert it. Check it out in the binary. Check it. Checked it. Checked. Do it. Why math error in the calci? Check once again. Check once again. You are getting math error. 65,535. You are getting math error. Okay, I'll do one more thing. 32,767. 32,767. 32767. Same. Math error. Showing the value. Binary values. What is the binary value showing? Zero, 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 zero. 1100, 1100, 1100. Is this what you are getting? Is this the value? 32767. 32767. 0111. Correct? Is that correct? Yes or no? I'm not used the calculator since 20 years. How much you want to get? 0 So we are getting 1 1 1 as a reminder. We are getting. Okay. See, these things generally because of calculator, because of the technology that's coming into picture, we are not used to. We are mainly depending on the calculators. Totally depending on the calculator. And my point here is when I am giving the value, 32,767 if you give, what is the value of getting? 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Is that what you are getting? 32,767 you are getting this. 32,768 you convert it. 32,768. Matter.
Because it is exceeding more than 16 bits.
Definitely. It is exceeding more than 16 bits. Seven six eight. Are you getting the answer? 768. Yes. Good. So this calculator is a 32-bit processor. He is able to get value. The calculator is FX991EX. FX991EX is a 32-bit processor. You can use the 32-bit data. What is this? Okay. You got that? Yes. This is exactly yes. Yes. Can we come back? Now it made you to discuss with respect to your calculator and what is the type of the processor you are having in your calculator. Some of you are having older versions, some of you are having the latest version, some of them are having 16-bit processor, some of them are having 32-bit processor. So if it's a 32-bit processor, it's going to take all the 32-bit value. Now, those who are having the calculator, that is EX, in that one, 65,534. 65,534. 534. You are able to get the answer? What is the first bit? First bit is 0. Leftmost, MSB. 0. First one is 0. All the remaining? Okay. You are getting it. Okay. Listen. You are able to get FFFF. Manually you are getting, but in calculator I am talking about. In calculator, are you able to get FFFF into hexadecimal? 65,535 into hexadecimal. Sai Rangaya, convert FFFF you are getting. FFFF you are able to get that one. So all bits are 1111 only. Okay. So it's a 16-bit. It is 16-bit. But if you go for 32-bit, 65,535 into 65,535. That is 32-bit. Archana, Priyanka. Excuse me. Hope we can come back to the topic. Now, You can exercise the different types of operations using your calculators. Where the calculators, what exactly is there in your calculator, the same thing is available in your PSRs. PSR, if the answer is negative, assume that one, the input what you have given is negative number, because the input what you have given is negative number. At that time, the 31st bit, that is MSB, that will be indicated as 1. The bit will be 1. If it is positive number, then the MSB is 0. If it is negative number, MSB is 1. I have given 55. So 55 is a positive number. My MSB, what I am having, bit number 31, it is going to be 0. This is 0. And 55, I will add some values for the 55. That will be indicated something like this. Value of 55 will be indicated. MSB is going to be 0. Assume that my input is minus 55. I have given the input is minus 55. So, minus 55, the MSB will be 1 and remaining values will be written as it is. This 1 indicates the value what you are adding is a negative number. Sometimes I will be giving positive numbers only. I may be performing some arithmetical logical operations in my program. Like I'm going to divide, I'm going to subtract, I'm going to multiply, I'm going to get some trigonometrical operation, I'm going to do some logical operation. After that, my answer is going to become negative. My answer has become negative over this. So as soon as the answer has become negative, if it is 0, the PSR will become 1. MSB of the PSR is going to become 1. Take an example. I have given 25. R1 is 25. R2 is minus 50. R1 is 25. R2 is minus 50. What I will do? 25 plus 50 I will do. R1 plus R2. R1 plus R2 I am doing over there. Result will be minus 25, you are going to get that. Immediately your PSR, the MSB of the PSR is going to become negative over there. Okay, previous thing was positive, then MSB of PSR is going to be negative. How to check this? In your Keel software, on the left hand side you are going to get the list of the register R1, R2, R3, R4, R5. At the bottom of that one, there is one more register called CPSR. I am having registers list R1, R2 like this. Here I am going to have CPSR, I am going to have PSR. When you enlarge that one, when you expand CPSR, here I am going to get N, Z, C, B and Q. All those things will display. This will show whether it is positive, whether it is 0, whether it is carry, whether it is overflow. These bits will show you that the value. If it is negative number, this will become 1. If it is positive number, N will become 0. Assume that one we are getting the result is 0. Neither positive nor negative. So at that time, Z will become 1, N will become 0. Okay, Z will become 1, N will become 0. I cannot have both N and Z is same. If N is 1, Z should be supposed to be 0. If N is 1, Z should be 0. If N is 0, Z can also be 0. It is not negative, not 0. It is positive number. But if it is negative number, it cannot be 0. If it is a negative number, the answer cannot be 0. Similarly, if it is a positive number, it can be 0. 0 indicates either it will be positive or negative. So negative cannot become 1. N cannot become 1. Okay. So I am having the list of the registers. Below that one I am having the PSR, CPSR. When you expand that one, I am going to get NZCV. NZCV indicate that one whether the carry has been generated or not. Assume that when I'm multiplying two numbers and when you multiply that one, the result is beyond my scope. It has generated a carry. So at that time, value C can become 1. If there is a overflow beyond 32 bit, my answer is generated. At that time, V will become 1. So it is not that one only R1, R2, R3, R4 you have to check that one. You should also check with the CPSR also. You should also check with the whether carry has been generated, at which point the carry has been generated. Only when you multiply second bit with the second bit, when you multiply second bit with the second bit, there may be a carry. When you multiply fourth bit with the fourth bit, there may be a carry. When you multiply last bit with the last bit, there may be a carry. We cannot say that from only at the beginning only there may be a carry. Each bit when you multiply, there may be a carry. Or when you each bit when you add, there may be a carry. Then maybe, or there may not be. 1 plus 1 is equal to 1, 0. The carry has been generated. 1 plus 0 is 1. Carry has not been generated. So, depending on the type of the bits, there may be a carry in between. There may be a carry from the LSB, there may be a carry from the 4th bit, there may be a carry from the 8th bit, there may be a carry from the 16th bit. Anyway, it can be a carry. So, carry can keep changing over there. When even in between, I'm not telling the entire program. In between only there may be all these things keep changing over there. R1, R2, R3, R4, 4 registers are there. R1 plus R2, there may be a carry. R1 plus R2, there may be a 0. R1 plus R2, there may be a negative number. Okay, so each instruction is keep changing the NZCV value. Keep changing depending on the type of the instruction what you are going to use. Yeah, you ask me. Overflow. So that's what you. There is a specific difference is there with respect to overflow and carry. I'll explain that now exactly. So NZCV, the first 4 or first 5 MSB bits are very important when you are performing the arithmetic and logical operations. Okay, even it may be read instruction, it may be write instruction, it may be arithmetic, it may be logical, it may be any type of the instruction. These are very important. And there are 3 more bits are there. IFT. Yeah. Are you able to see IFT? Rightmost corner. There is M0 to 4 is there. After that one, IFT is there. Okay. I indicate interrupt. F indicate fast interrupt. T indicate thumb instruction. I indicate interrupt. F indicate fast interrupt. And T indicate the thumb instruction. That means if T is 1, if the bit T is 1, you are not using the arm instruction, you are using the thumb instructions over there. Thumb instruction, it may be given with 16-bit data, it may be given with 32-bit data. Okay, so you have to be very careful. What is the value of this? So we are able to see NZCV, Q. We should also know that one whether I is there. If I is 1, there is an interrupt has been generated. If F is 1, a fast interrupt has been generated. If T is 1, then it is a thumb instruction, it is not the arm instruction. So all these things are very important. NZCV and other bits like 27, bit number 8 to bit number 27, bit number 8 to 27, almost 24 bits, 20 bits, they are reserved for the future use. Reserved for the future is then IFT, interrupt, fast interrupt and thumb instruction, and M40 to 4, that is 5 bits are there, that is for memory purpose it's going to be. Okay, this data. If you compare this with the current program status register in ARM7, you might find that some bit fields that were used in ARM7 are gone. ARM7, whatever they are using, it's gone over this. Comparison of the some CPSR in traditional ARM processor is shown. This is what the CPSR bits, which is there in ARM7. That's what IFT I'm finding it out. So ICT, I'll see here, it is there. NZCV, negative, 0, carry or borrow, overflow, Q, sticky saturation flag, ICT or IT. interrupt continuable instruction. Interrupt continuable instruction, that is if then instruction status. If else, there is an interrupt. If is creating an interrupt over there. If this is condition is true, go here. If condition is not true, go somewhere else. That is an instruction which is generating the interrupt. T, some state, always 1, trying to clear this bit will cause a fault exception. If you're trying to create, always it will be 1. Automatically it will switch between ARM instruction and also thumb instruction. T is supposed to be 1. Exception number indicates which exception the processor is handling. Which is the exception the processor is handling over there. Hope I can stop it now. Because lot of things are there to discuss about CPSR. I'm going very slow with respect to CPSR.